We are going to start. Good morning, everyone, and welcome to our first 2cool2waste cluster webinar. So this one is called Boosting Energy Efficiency in Industry, and I'm happy to kick this first webinar and introduce you first the 2cool2waste project cluster. So what is 2cool2waste? We are a community of 15 Horizon Europe projects that are driven innovation in renewable heating and cooling, waste, heat recovery, and thermal energy management. And our mission is clear. So our mission is to boost energy efficiency across industrial and buildings. Also to promote low-carbon electrified heating and cooling system and share knowledge, events, and collaborative initiatives. So by joining our forces, our project aims to turn innovative solutions into real impact across Europe. And together we are tackling the challenge of decarbonizing the industrial and building sectors and making energy use smarter and cleaner. And also through this cluster, we will have access to the infos, webinars, events in sustainable heating and cooling. So please make sure to follow our pages, our social media, and stay updated. And we are really excited to share the solutions and business cases with you today. So I hope this webinar will spark new ideas and maybe collaboration and actions that contribute to a more energy efficient and sustainable Europe. And thanks a lot for joining us, and let's get started first with GEOSYN.
Okay, so good morning. I'm Paride, and today I'm going to talk about this the GEOSYN heat pump. The agenda for today is basically to talk a little bit about the heat pump we are developing in our project, and then briefly describe the selected case study, the results related to this case study, and finally state the conclusions and the future work. Yes. So in this slide here, you see the schematic of the simplified version of the schematic of the heat pump we are going to develop in our project. And you can see that we have 4 stages of compression, some intercoolers in between. And the idea is to connect the heat pump to the geothermal well in Italy. So the geothermal well will be basically the heat source. And when it comes to the heat sink, the target is to reach heat or to generate heat up to 100 and up to 200 degrees Celsius. Now, yes, so the refrigerant will be water, and the compressors are novel compressors, variable speed, and all-free piston compressors, whose maximum discharge temperature will be around 270 degrees Celsius. Now, the target of GEOSYN, at least when it comes to the heat pump, are basically to demonstrate and achieve TRL of 5, and also demonstrate some startup and wrap-up strategy, and make sure that the COP will be always higher than 3. Let's see the selected case study, the selected energy-intensive industry. So the results I'm going to show are based basically on a dairy facility, which needs heat up to heat at 186 degrees Celsius. And currently they're using a boiler with natural gas to satisfy the heating demand, which is more or less equal to 2 megawatt. And when it comes to our results, basically what we did was to use the real field measurements of the real geothermal well as an input to our model and select a specific day. And finally, we also used some dynamic electricity price, so over the 24 hours, real values, and also the real values for when it comes to the price of the natural gas. And I also need to highlight that all the results will be based on this model here. You see the schematic. We don't have time to go through the schematic, but it basically is what we did was to implement an advanced dynamic model in MATLAB SimScape. So all the results will be based on this model here. Now, If we have a look at the results, what we got basically is that, okay, so on the x-axis we have 4 graphs here, and on the x-axis of each you have time, so the 24 hours. And you see, first of all, at the top, you have the temperature of the geothermal well, real values, so field measurements. But what we are interested in here is the sink outlet temperature, because we said that we want to provide the dairy facility with 186 degrees Celsius. And you can see that we achieved this target in the whole 24 hours. And we also said that we want a COP above 3. And you can see also that, again, the COP is above 3 the whole day. And also we want to provide the 2 megawatt, and you can see that in the bottom, again, we achieve this 2 megawatt over the 24 hours. I can also show you that in terms of operating cost, if you see the results on the left, let's say, you have that the green bar is much lower than the red bar, so means that we can save 24% of the costs over the day using the GEOSYN heat pump compared to the boiler in the selected day. Now, the following examples refers to when the prices goes up by 24% and 40%, pardon. And I just want to mention that even if the electricity price goes up, increases by 40%, and the cost of the natural gas increases only by 20%, still the high temperature heat pump is more beneficial from an economic point of view compared to the boiler. And finally, back this graph at the right bottom, we have the greenhouse gas emissions. And you can see that over the 24 hours, the high temperature heat pump can reduce the greenhouse gas emissions by more or less 73% in the selected case study and over the selected day. So conclusions. So first of all, I would like to say that by using the GEOSYN heat pump in the selected case and the selected day, we can reduce the operating cost by 24%. And at the same time, also reduce the greenhouse gas emission by 73%, which means that potentially our heat pump can replace the boiler. Yes. And as a future work, we are going to keep working on this heat pump, in particular to keep developing and demonstrating this heat pump until we achieve a TRL of 5. And we will install this heat pump again in this geothermal well in Tuscany, Italy. And before give the floor to my next colleague, I just would like to thank all of you for being here, the organizers, but also my colleagues in this, all the partners in this project. And in particular, I need to give credits to Vaishak, my colleague Vaishak, who is actually the main driver and the guy who made the models and got all the results in this project. And finally, I hope I'm in time. Thank you for the attention. And if you have any questions, I will do my very best to answer. And thank you for the support, and sorry for the technical issues. Sorry.
Thanks a lot, Farid.
Thank you.
And now we have HEATWISE.
Okay, I thought I will share. Thank you for sharing. Hello, everyone. This is Çağatay Yılmaz from Rice Research Institutes of Sweden. We represent HEATWISE project here, but more or less the findings that the vision that I want to share in this limited time, it is consisting of a series of different EU fundings, and I will try to step by step explain and walk through with you how we are actually trying to turn this market into a more efficient market. Yeah, we can go to the second slide as you did. We have a big risk in front of us. I usually this graph is highly anticipated by some experts, but this actually symbolizes one thing, regardless of the values that you see here. In future, we have a few options in front of us, and you can see, I will walk through with you, there are different colors. The first option is the green option, where in an ideal world, with this increased amount of digital technologies consumption nowadays, the data centers in the Europe, they will be more and more energy efficient, and their consumption is going to drop down. So for us, this scenario is an impossible scenario. Like in a world that everything is possible, this is the best case scenario that all our efforts to make data centers more sustainable happens in the right way. A more realistic diagram is the dark blue one on the top, which is showing us the trend of how data centers energy consumption in Europe is rising. And there is the worst case scenario, which is described as red. And everybody is worried. Maybe you're aware of that. In some countries, people even started protesting against the data center investments, because in some countries like Ireland, they actually started to be equal to 17–18% of their whole country's power consumption. And it is affecting the grid drastically. So what we are talking about today is the brown line that you see here, which is related to edge computing, distributed computing paradigm's effect on the market. Can we go to the next slide to understand edge computing a bit better? I participated in multiple EU projects focusing on edge computing. Many experts say it in different way, but let's consider that now we actually carry it step by step in the last years. All our compute and storage power into centralized locations because they were safer and they were more efficient. But now the emerging technologies of today, they are actually pushing us or making us to push the compute and storage closer to end users. Just think about it. How many actually smart devices that you assign to your home network or work network in the last year? So this drastic increase of the Internet of Things and the data generation makes us create a distributed computing paradigm, and actually there is no upper and lower limit for that. Some of the compute devices, they start with a few kilowatts, and some of them reaching a few hundred megawatts. So it is not really easy to distinguish what is edge and what is centralized compute anymore in today's world. So it is making it's really critical for us to come up with some dynamic grid integration of data centers. Otherwise, we are really big loads on the grids, and we have a byproduct which is heat, and if it is not being used, then we are being a big burden on the grids itself. We can go to the next slide. So what we are doing, okay, there are some animations. Our idea is replacing the boilers of the buildings and districts, because anyways we consume this energy, anyways we have this byproduct, and the best way to make the system as efficient as possible is to reuse the waste heat. It is not that easy though, because the districts and the buildings, they have some requirements when it comes to the waste heat that they can accept, and the temperature requirements, because most of the data centers, they can send back high degrees as a return temperature. That's why we listened the previous presentation. We need some step up in the temperatures. But if you use the right technology in most of the cases, without needing any extra heat pumps or other systems, we can actually make this returned waste heat useful for the buildings and districts directly. Can you press the next one that I can show? Yes, return temperatures are really critical, and how we want to tackle this issue is we are using a direct-to-chip pool type two-phase direct-to-chip boiling system to control the boiling temperatures and get the highest return temperatures as possible. You can go next again, yeah, one more time. And while doing so, we are building a data-based management system which orchestrates both the cooling system and the IT load. By doing so, we make sure that we are getting the best performance out of IT while providing the best cooling to IT as well. Giving the best product lifetime longevity. Yes, we can go on. Yeah, we can go to the next step. Obviously, one of the things that we endeavor here, we don't have the same heat demand all year long. This actually graph shows our own buildings' heat demand through the years. We live in Sweden in a really cold area. You see, summertime we really don't need any waste heat, but wintertime we require a lot of waste heat. So this is one of the things we are trying to tackle. And next slide, please. Sorry that I bothered you. And as discussed, this can only be solved with smart systems with the minimum human interactions, where data flowing from all grid representing the building and district and the data center itself. And press one more time. So by doing so, we can understand the heat demand of the building and the district, read the renewable percentage in the grid. One more next. We can read the energy price and carbon density. And next step would be then by reading everything and train a sophisticated digital twin, which actually makes the right decision for you and controls the data centers as a holistic way, both IT systems and the cooling system itself to operate it with the maximum efficiency. Okay, 5 minutes. I don't know if I hope I didn't.
Perfectly on time.
Oh, okay, wonderful. If you have any questions, I will be here anyways.
Thanks a lot. We will have time also at the end to, if you want to ask questions. Okay, thanks a lot. And now, Hycool-IT.
Hello, good morning. My name is Marcello Aprile. I'm the coordinator of the Hycool-IT project, and today I would like to give a short overview. Hycool-IT means hybrid cooling and management for IT infrastructures. What does that mean? Well, first of all, the motivation for this project, we know that we have big data centers, as we've seen before, but also we have a lot of small server rooms in Europe. By small, I mean about 25 racks on average, which are typically quite energy intensive. We find this in hospitals and universities mainly. In terms of peak power and operational time, and normally the efficiency of a cooling system is not the best ever. A conventional computer room air conditioning system is used. And the waste heat normally is not recovered or exploited. So to face these challenges, we are working on mainly two aspects. The first is about the management. So as we've seen before, digital twin is certainly a fantastic solution to optimize design, operation, and maintenance in these server rooms, perhaps including waste heat recovery. And we are doing that following a standardized approach for energy modeling, because the effort in modeling system is quite huge, and we would like to make it in a way that is reusable in the future. And the second aspect is how to improve, let's say, the energy efficiency of the cooling system. And for that, we're working on a rack integrated absorption chiller to cool liquid cool servers and at the same time provide in a free manner air conditioning to the server room. I will explain this in the next slides. So the first is the building digital twin as a platform as a service, which is basically bringing together monitoring data and simulation data. And we identify two main areas on the functional level. One is on the right, is the simulation model tracking system, where we want to basically compare monitoring data and simulation data in real time. And the other functional area is model predictive control, which basically use surrogate models to optimize the operation of the system. All this is made possible by an architecture that is conceived to operate in real time. This is the main challenge. And that is basically the main effort we are facing in creating an architecture that follows standards and use effectively, let's say, tools on the web, which allows integration of different devices and provides the ability to communicate with simulation tools. Next, please. And concerning the second aspect, direct integrated absorption chiller, the idea is to reuse the heat generated by servers that we see on the left, on the bottom left of the image, the green lines. This heat can be at temperatures suitable for activating absorption cooling systems that can then be used to generate cooling that is normally required in liquid cooled servers to cool other devices that we have in the racks, like, for example, disks and so on. So basically, we have we are working on a compact, self-contained, and cost-effective way to provide cooling. And however, this is not easy, of course, to achieve. The design of absorption chiller had to be completely changed. I mean, not the usual way because of the space constraint. And what you see on the right is an example of a proof of concept where we see that how compact the machine is, and this can be clearly installed in the back of a rack. With this, we target power user effectiveness in the range of 1.1. Next, please. And finally, a few words about our pilot case. It's a pilot building undergoing renovation and including a waste heat recovery system. Basically, we are following a big renovation project that involves renovation of a server room using more effective heat exchanger for cooling. That means we can work with higher temperatures of a chilled water. Renovation of the cooling system. That means we can use better free cooling and increase efficiency at partial load operation. And we're also renovating the building itself to limit the heat demand in winter, especially the peak. Sorry, I need 1 second more on the previous slide. But the most important thing to mention is that we are performing waste heat recovery here. So the server room can provide heat to a near building. And with that, we count to save like 20,000 euro per year. And this saving is enough to justify the investment on a waste heat recovery system. And all this will be controlled and optimized through the building digital twin architecture that you see an image in this slide. So that's all for this short presentation. I would like to thank all the partners. We are 9 partners from 5 countries, and please feel free to contact us for any questions. I leave my contacts.
Thanks a lot, Marcelo. Right on time too. And now I'll let the floor to Moderator.
Hello, can you hear me?
Yes.
Okay, perfect. Hello all, I'm Dimitris Koutsanikolas. I'm project coordinator of the Moderator project, and I'm coming from Center of Research and Technology Hellas, and I will try to quickly present you the Moderator project and its approach to heat recovery and utilization in data centers. Next slide, please. So, yes. Probably you all know, and you heard before, the current trends with data centers and their rapid evolution over the last years. You can see the graph in the right that data centers globally have huge energy demands and consume more electricity many times than entire countries. These graphs are 5 years old. The situation now is worse and will become worse and worse with the recent expansion of AI. Improvements in energy efficiency have reached probably their limit. So even with very efficient cooling systems, which have very low energy consumption, all of the installed IT power in data centers will be converted into heat. So there is plenty of waste heat available out there, but this is currently just released to the environment without any exploitation. And why is that? There are two main reasons for this. One is that the heat produced mainly in conventionally air-cooled data center is of poor quality, meaning low temperature and diffuse. And also that data center produce more heat in the summer, while most of the times we need this heat in the winter. At least for district heating applications. Next, please. So here you can see the moderator approach, and what we propose is an integrated approach to waste heat reutilization using the immersion cooling system as a game changer. What is immersion? Yeah. What is immersion cooling? It's a system where all the electronic components are immersed in the electric liquid fluid, which is used to cool them down in a much more efficient way than conventionally air-cooled data centers. The generated heat in the liquid can be easily recovered and then either can be directly exploited or stored in some novel heat storage systems that we developed in the project, and I will show more details later. And this way, both of the main obstacles that hinder heat reutilization can be effectively tackled with this approach. Next, please. So here you can see some more details about the Moderator project, and what we are targeting is the development and demonstration of an integrated prototype unit based on 3 key elements: the immersion cooling system itself that cools down 40 kilowatt of installed electronic components, an innovative heat storage system based on phase change materials, specially tuned to recover heat in the selected temperature range, and the highly efficient insulation system to allow for prolonged heat storage for prolonged periods. The overall system is by design modular, simple in operation, and sustainable in use. Next slide, please. Yeah. Another important thing that we are looking in Moderator project is to identify the best potential end users who can efficiently use the recovered heat, taking into account the size of the data center, its location, the achieved temperature in the system, the required temperature by the end user, and several other factors that can affect the decision. Currently, we are assessing both applications for district heating networks using also heat pumps to upgrade the recovered heat. Next slide. As well as several industrial or commercial applications like the chocolate industry, pulp and paper industry, greenhouses, which is actually a very good case study for the recovered heat in this range. And we will assess and identify the best solutions depending on the developed technology. Next slide. So this is our consortium. We are a consortium of 11 partners with 3 research organizations and 8 SMEs all around Europe with distinct expertise in this area. Next slide. So yeah, I think that's all. For any questions or for any information that you may need, you can contact me anytime or find more information in the project website. Thank you.
Thanks a lot, Dimitris. Time to push to it.
Hello, everyone.
Hello, Carolina.
Okay, this is Unlocking Waste Heat Potential with Push-to-Heat Solution Strategies and Business Models for Industrial Decarbonization. So first, we will go to a Push-to-Heat project overview, main technologies, pilot sites, and defined use cases. Then I will go to define a case study we developed for a paper that will be soon presented. Okay. Push-to-Heat project main objective is to unlock the market potential and develop viable business models for heat upgrade technologies in key industrial sectors. This will promote market uptake through viable business models addressing technical and also non-technical barriers to enable broad adoption throughout Europe. The demonstration on this project is through 4 full-scale pilot plants across different sectors and industrial applications that in average are based to convert waste heat between 40 and 90 Celsius degrees into useful heat at 100 and 160 Celsius degrees. Why is it focused on industrial sector? Because this is one of the major energy consumers in Europe, and of all the primary energy consumed, up to 20 to 50% of the primary energy is lost as waste heat on the process. Below you have a table in which, through some waste heat factors, have allowed to estimate the theoretical potential of waste heat. This depends on the amount of energy consumed on each sector per country, the characteristics of each sector that have been taken from literature review, effluent losses, temperature and ranges. And in this table, you can see that main sectors are the first one, iron and steel, then chemical and petrochemical, followed by food, beverage and tobacco, and pulp, paper and printing, having a great amount of terawatt hour source of waste heat in Europe. In this case, Push-to-Heat has 4 main technologies that can be classified in electrically driven heat pumps and heat transformers. The first ones are convert waste heat into useful heat with compressors. We have 1 piston compression and 1 turbo compressor. Then the other ones utilize thermal gradients to recover and upgrade this waste heat, operating primarily on thermal energy with relatively low electrical consumption than the previous one. In this case, we have an absorption heat transformer and a thermochemical heat transformer. These technologies have been applied in, no, next one, please, into 4 main pilot sites. The first one, piston compressor, has been installed in a paper industry, which is recovering heat from 40 Celsius degrees to 120. The next one is more or less being still defined due an amendment, but is going to be a turbo compressor for a paper industry that will recover heat from 90 to 115 Celsius degrees heat. And then absorption heat transformer for paper industry will recover from 90 to 140 Celsius degrees with lower electricity consumption. And last one is thermochemical heat transformer that will be installed in a chemical industry. And then in this project, we have defined different use cases that represent different heat recovery configurations. First one, and most interesting, would be to recover the heat on site on the same process. Other The next one is to recover waste heat from one facility to be sold to another neighboring facility. Other possibility would be to recover waste heat from data centers to an industrial site, also waste heat from district heating networks, and lastly, industrial waste heat to be an input for district heating networks. In this case, we have chosen use case 2, which is to recover waste heat from one industry to another. And we have developed a techno-economic analysis for the integration of a high temperature heat pump. So to replace a conventional gas boiler with a high temperature heat pump. First, we quantified the potential, and then we chosen 5 processes from different energy intensive sectors. This is based on an analysis made from 5 industrial sites in Spain with operative data for 2024. This is focused on energy performance, economic viability, and environmental impact. So we have chosen cement industry, the first one, a kiln, chemical industry, refinery operation, paper sector, which is thermal drying, food sector, a pasteurization process, and lastly, food sector also with alcohol condensation. You can see in the table that all of them have different process capacities and source temperature, and also different running operation hours. The first step was to quantify the amount of available waste heat was available for being recovered, as you can see in green, the waste heat, and the COP that the heat pump will show on each case. Then we perform an economic analysis and environmental analysis. In the table below, you can see the expected energy savings due to the replacement of the heat pump, and thus the CO2 savings and OPEX savings, also installation and payback. From this table, we can highlight that the most efficient case is case 1, cement industry with a rotary kiln, because it has highest source temperature, 90 degrees, and sufficient waste heat capacity, more than 2 megawatts, with a good COP, so a good performance. The better economic performance can be seen in chemical sector, but the case 3 shows no OPEX benefit because the temperature is so low, it's 43 degrees, and even though it has great capacity, it does not have sufficient temperature to generate some savings. Then the greater decarbonization potential is case 5, which was the one with more operative hours and also has good waste heat capacity too. So, well, as conclusion, to sum up all of this, we can see that industrial sector has large untapped potential. So it is a major opportunity for decarbonization. Major sectors are chemical, food, non-metallic minerals, iron, steel, and pulp and paper. We can see that there is proven technical feasibility, for example, with this high temperature heat pump case study. So high load, high temperature process has a great potential and also favorable paybacks. And as always, policy must be a key enabler to effective waste heat recovery deployment, but it also requires sector-specific strategies to adapt better to the operation temperature and to better estimate the waste heat capacity. And that's it.
Thanks a lot, Carolina.
Thank you.
The floor to Rich.
Yes, hello everyone. Good morning also from my side. I'm Michael from Dr. Jacob Energy Research, a German partner in the REWITCH project. And I want to present you the REWITCH project focusing on renewable and waste heat valorization in industries via technologies for cooling production and energy harvesting. The project itself, it's a European Horizon Europe funded project for a total duration of 4 years. Soon we already have half of it by the end of the year. The project consists of in total 26 partners across all over Europe from 10 different countries, and also includes partners from UK as well as from Switzerland. The project itself focuses on different objectives and different tasks to provide clean and innovative cooling solutions for the industry. First of all is to consider techno-economic integration for real demo cases. So the project has 4 demo cases in 4 different countries, in 4 different sectors. And we will integrate high vacuum flat plate collectors as well as use waste heat from industrial processes to drive absorption chillers. We focus on 2. So across the 4 demo cases, there are 2 adsorption chillers as well as 2 absorption chillers. The adsorption chillers will be innovative solutions on focusing on cost effectiveness. The absorption chillers, there are 2 solutions and they're innovative ones. One is a double evaporator chiller. So this absorption chiller will be able to provide cold at 2 different temperature levels for the users with 1 machine only. And the hybrid compression absorption chiller will not only deliver cold, but also heating as on a good temperature range of around 60 degrees for preheating purposes for process heat. On the high vacuum flat plate collectors, they are provided by REWICH partner TVP. And other than other flat plate collectors, they will be able to deliver heat at a temperature level of around 200 degrees. So it will be very suitable for industrial processes. Within the project itself, they will be used to drive the absorption chillers. Additional activities that are also ongoing at the moment in the project are, first of all, the digital twin development. So here we collect information based on 2D equipment models as well as local site drawings, different information collected via Excel, but also additional site information, also construction-wise, and integrate all those information in the BIM project to create those digital twins where you can already see that the pipings and the 3D drawings are in the making. Also, we're performing simulation studies to actually analyze in depth the energy and thermal performance of the systems to investigate what is the benefit and the size of the thermal energy storages in the system, especially focusing on the solar thermal applications, as well as in general the heat to cold conversion. I already mentioned that there are 4 demo sites. First one is a brewery in Poland, where the waste heat is from the local wort is used. The wort has a temperature of around 98 degrees. It needs to be cooled down to 8 degrees. So here we use SENERGY from the wort as a heat source, as well as the medium to be cooled. In Spain, REWICH has another demo site at the food company of Covap, where we integrate this hybrid compression absorption chiller. In Greece, the demo case is focusing on biomass and biofuels. Here, heat is from the solar thermal collectors, as well as waste heat from the local digesters and CHP units will be used. And the 4th demo case is in Italy, in the paper and pulp production, where we use the waste heat only from different compressors on the site. An additional topic or additional project is the Exquisite project. It's also a part of the 2cool2waste initiative, and the project just started or kicked off yesterday. It's a new project, and looking forward for more activities, more collaboration within the initiative. Thank you very much.
Thanks a lot. I let the floor to Sid.
Thank you so much. Yes, I'm a coordinator of SEEDS. I'm going to take 5 minutes to introduce you the SEEDS project. So I'm an associate professor at Department of Civil and Mechanical Engineering, DTU, and I'm also operating agent for 2 annex under IEA EBC 82 and Annex 96, focused on energy flexible buildings. So for SEEDS project, it is a larger project that was kicked off January 1st, 2024, and it's a 4-year project. So with the SEEDS, we aim to develop a renewable energy-based smart heating and cooling system to phase out fossil fuel in heating and cooling system in Europe. For that, we have 6 pilot sites in 5 countries and with 25 partners. So it's a larger consortium because this is focused on domestic use of heating and cooling system, and we also have a local ecosystem in each pilot site. For that purpose, each pilot site has at least 2 or 3 partners. Next slide, please. So here is a overview where we are. So in Denmark, Belgium, Slovenia, Hungary, and Greece, we have pilot site demonstrate different type of solutions, and we also have follower site from Ukraine, and we have also partners from France and Italy. So it's a very large consortium, and at the moment in 2025, the 6 pilots are in the phase of construction installation and also gathering data. Different pilot has different progress so far. I will go in details later. So 6 pilots, there are 2 in Belgium. Both are cultural heritage houses in historical site in Bruges. And so on the left side, the graph shows one neighborhood where the smart heat pump system with the MPC controller has been installed and demonstrated. And this solution will be replicated on the right neighborhood, which is also a cultural heritage neighborhood. So on that side, we have in-project replication. For the Hungarian pilot site, we have a very old apartment block where renovation for enhanced energy efficiency is very important. So we're going to do a lot of retrofitting for the building facade, including adding more thermal insulation material, replacing window. At the moment, the replacing of window has been finished, and there will also be BIPV installed on the building. So in the Greece pilot, it is a dormitory building in the campus where 20 of the rooms have already data collection sensors installed and the data infrastructure implemented. The campus is provided by a multi-source renewable energy integrated heat pump with the geothermal and the solar thermal integrated. And here we're going to demonstrate the optimum use of the multi-source, provide better indoor thermal comfort as well. For the Danish pilot building, it is the only new building. The construction phase has been finished, and from beginning of July this year, this office building start to be used, and all the space has been rent out. People moved in. Data collection also started. So in this office building, we have a very modern BMS system, and our work will be utilize the BMS system to conduct advanced control for the cooling system and the heating system, to deploy demand-side flexibility, utilize a variable electricity price. For the district heating side, my team has developed the method to design variable heating price that we're going to test in this building. And additional to that, we also have a dialogue with the district heating company where they will implement dynamic heating price at scale. Then in the Slovenian pilot, we have 5 petrol stations. So the energy company who own the petrol station is a partner, and they're going to include these 5 petrol stations in the portfolio of their flexibility provider. So overall, those flexibility from the 5 petrol stations will be part of the aggregate profile. Then they're going to utilize to bid on the electricity market. So for the Slovenian pilot, the main work is actually develop automation system architecture and the trading platform to support the aggregate deploy flexibility from small distributed energy resources. So this is just an example of one of the control architecture. This is the Danish building, where the Dundee Business Park is the building owner. Nordmatic is the BMS provider, and we collect data from them to a data management platform that's Center Denmark. And through their platform, all the researchers and the organizations who provide the control algorithm on forecast use that data to provide input for developing controller. Then the controller will be implemented back to the BMS system. So for the building with 5,000 square meter, we have 1,010 measurement points with a 1 minute time resolution. So we already started to collect data from July 1st. Next, please. Yeah, so I'm the project coordinator. Anais is our communication manager. If you have any questions, reach out to us. Thank you a lot.
Thanks, Rongling. And now it's time to SENERGY Nets.
Yes. Hello, everyone. I hope you can hear me well.
Yes.
Perfect. So thank you very much, Anais, and also welcome to everyone from my side. My name is Renato Luise, and I'm energy engineer, and I'm the coordinator of the project SENERGY Nets. As you can see in the next slide, first of all, maybe a short introduction to the project, since it is a 4 years long project, and we are right now entering the last and the 4th year of the project, which means that we are right now in a very hot phase of the project, producing many results. And also, since we have 3 demo sites, we are really starting to apply our models to those demo sites, and also to additional case studies that I will introduce soon. But first of all, I mentioned the models. Why? Because if you look at the target of the project, basically what we want to do is to optimize the planning and the organization of the district heating and cooling system, and also the distribution grids with the MES models. MES, of course, multi-energy system models. And what we want to do with our models is really to gain, to win, to enhance the flexibility. So we will really talk about winning, gaining, buying, selling flexibility, and also, of course, facilitating the sector coupling for the services between the DSO and TSO, so between the distribution and transmission system operators. If you can see here, the other target, of course, as you can imagine, is a horizon project, is the decarbonization of the energy sectors. But how do we plan to do that? So basically, I already mentioned you multi-energy system modeling, optimization. We want to decarbonize the heating system, the cooling system, and the electricity. Of course, you can imagine district heating and cooling, those things are all connected, going all together. And of course, according to the demo site, we have different options. But let's say generally what we can see is that, of course, sector coupling and integration plays a fundamental role. The implementation and also the measure higher use of renewable energy sources produced locally will help us to achieve this scope. And on top of it, I will show you later in the demo case studies, we also have different generation of district heating and cooling, which will allow us also to experiment, let's say, new solutions. Here's a very general scheme, but I think that everyone is pretty, how to say, confident with that. So finally, we can see that from both sides of the scheme, we have from one side the low carbon electricity production that can be given by, of course, renewable energy sources, nuclear electricity, which is once injected into the grid, ready for the power to it solution. And on the other side, we have also other application where not only renewable are used, but also like renewable fuels, biofuels, and solar power. In this case, we will enable the production of low carbon heat and electricity production. And all of this, you can imagine that is converging, let's say, in the solution of the district heating and cooling. If you go to the, and that's how finally we get the flexibility. So these are all the options we are investigating. And of course, according to the geographical approach, to the generation of the system, the district heating and so on, we are experimenting. The next slide is a very sort of sum up of our consortium, just to show you how finally is spread among 8 different European countries and 19 partners. But on top of that, we are really proud to see not only many research and academia partners, but also energy supply and services partners. And on top of that, of course, we have the possibility to work together to 2 DSO. So one is from the Slovenian partner, Electro-Ljubljana, and one is from the Italian one, Moderator. And also in our advisory board, for example, there is the French TSO. It's not a partner, but still it's always really helpful to have feedbacks from TSO. And just for completing the consortium, we have also software providers and association and networks partners. I promise you to say a few words about our demonstrators. So the number one is the Italian one. It is in Milan, and it is a third generation district heating. So what is, let's say, the unique selling point of this demonstrator is basically the fact, as you can read also here, I will not go through all the numbers, but we are talking about more than 40,000 end user and more than 100 kilometers of cables. So the area covered is pretty big. And finally, with the use of this model that we are developing, we are really aiming to optimize the system, reduce the energy consumption, and augment in general the overall efficiency of the system. We already had some proof of concept, but also we really run the models this summer. So basically it was also possible to test them. And finally, we are soon publishing also some of the most important results that have been achieved in the Italian demo. The second demo, otherwise I took too much time, I have to speed up a bit.
1 minute left.
The second demo is the Slovenian one in Ljubljana, and in this case our main goal achievement is to move those district heating from the third generation to a fourth generation. So it's still a high temperature district heating, but finally with a higher energy efficiency. And the third one is the one that has the highest, let's say, it's the highest generation. It's a fifth generation district heating and cooling. Is in France, in Paris, and it's if the first two were more about the city, including different type of users. In this case, we are focusing on the Gate Montparnasse commercial center. So we have also in this case different requests for heating and cooling. We have offices, we have shops, we have a hotel, and finally, once again, with our model, we are really trying to optimize all the energy system efficiency. On top of that, not only 3 demo sites, but also 2 case studies. The first one is in Spain, in the city of Cordoba, and we are representing the Hospital Universitario Reina Sofia. And the second one is instead on Västerås in Sweden, where we are more focusing on a district heating area through the use of a CHP plant. As you can see here, it's just a sum up of all the models that we are developing. And as I said, we are already in a pretty advanced status of the project. So also for you, you can see that all those models that have been implemented in the so-called Panda Prosumer library, if you're interested, they have been launched and published. And you can see here now, it's appearing the website. Then just one click more. Yes, so the Panda Prosumer is online and it's open source. So whoever would be interested in trying make some proof of concept or validation also to help us using those models, there is the on GitHub, it's the list of all the models is online available, and we also have a bottom of this slide. You have also the link to the documentation in case you are interested in more and more detail. So with this slide, I am done. I think the question we keep for later. So just thanks to all the participants. And if you want to follow more updates on SENERGY Nets, there is also the LinkedIn page and so on.
Thanks, Renato. And now we are going to Spirit.
Thank you very much. So my name is Simon Spoelstra. I'm working for TNO in the Netherlands. I'm coordinator for the Spirit project. Yeah, next slide, please. So Spirit project is a Horizon Europe project with about 16 partners from. So we have end users, we have equipment manufacturers, we have RTOs, and we have also a couple of organizations working on non-technical issues, and an external advisory board. So the main objective of Spirit, you could say, is to make sure that industrial heat pumps are like the reference technology for upgrading heat to about temperature levels of 160 degrees. And to do that, we have 3 demonstrations in the project. And we also do some technology developments, also looking at modularization to get things cheaper, designing web-based tools for an end user to work, also on market studies, non-technical barriers, competency frameworks, and things like that, and of course also awareness. Because we have limited time, I only will talk about the technology work we're doing in this project. And we'll start with the next slide. This is the demonstration. So we do 3 demonstrations. So the first one is in the north of Norway at a prawn processing plant. And here they use currently LPG that's burnt in a boiler to make steam of about 140 degrees. And we will replace this with a heat pump concept, and that is supplied by Mayakawa from Belgium, the European office. And it's a cascaded system. So it actually consists of 2 heat pumps in cascade. So the first heat pump will take heat from like ambient temperature, but it's the condenser heat of the existing refrigeration system. So that dumps heat about 20 degrees, and that will be upgraded with an ammonia heat pump to 80 degrees. And then there's a pentane heat pump on top of that that will upgrade it to the steam required for the prawn processing, the cooking of the prawns. The power source is about 700 kilowatts of supplied heat, and the RTO involved in this case is TNO. The current status is that we had installed all the heat pumps and integrated, but we had an oil spill incident, what caused a setback, so things needed to be repaired. The next month, the heat pump will go back into to Norway, and we hope to do commissioning in end of October, beginning November, and then towards the end of the year, we'll be operating the heat pump. The second demonstration is in Belgium. That's a sugar mill from Tientje Suiker. Here, GEA supplied a heat pump, and it's using the waste heat from there's a multi-stage evaporator, and the last stage has a vacuum steam, which cannot be used again. So that heat is upgraded to temperatures of like 140 or 110 degrees. By the GEA heat pump that also uses pentane as a working medium. The size here is about 3.5 to 4 megawatt. And there are different temperatures here because they run 2 types of campaigns in sugar mills. So they have a beet campaign and then a thick juice campaign. And they use the high temperatures during the beet campaign and the lower temperature during the thick juice campaign. RTO involved here is DTI. The status is that we have installed the heat pump in spring, but the campaign was like ending then, so we had to stop. So it ran for like a week, 2 weeks. But we made some modifications, and currently the campaign is starting up again, so the heat pump will also be operating again. The third demonstration is in the paper production in Czech Republic at Smurfit Westrock. Here we'll do steam compression, so we'll make use of steam that is no longer used and upgrade this to a steam pressure level that is used in the drying cylinders of the paper production process. About an 800 kilowatt system here. Spilling is the technology supplier, and the RTO involved is DLR. The status is that this is on hold because we needed, because of financial and organizational problems at Spilling, we needed to have an amendment in place for having to continue with a new Spilling partner, and the amendment is now under signing, so we hope to restart this demo on very short notice. The next slide. Yeah, so all these demos are accompanied by modeling. So we have made both static and dynamic models. The static mainly for doing the conceptual design phase and to get some performance data. We also have made dynamical models for all the 3 demos, which are a great help in commissioning and also to optimize control systems. Also turned out sizing of components could be changed. So it was a great help, and we're also using these tools for other dynamic processes to see to use the same models also to do dynamical modeling on other cases. Next slide. Yeah, some technology development that we do in parallel with the demos. So we've been looking at the compressors, mainly at the screw and piston compressors, looking at materials, seals and oil and things like that, whether they were suitable for the high temperature and pressure conditions in these heat pumps, and did flow optimization studies for the piston compressor to see if you can design the flow geometry in a different way to get less pressure drop in the system and there with a higher efficiency. The compressor technology that is used most of the time is piston and screw compressor. They use oil as lubrication, and if you go to high temperatures, this oil can be an issue. So we've done studies on how you should select the oil given your conditions of the heat pump. Also made a paper out of this. We also looked whether you could separate the oil in a different way than currently done, and identified some technologies there. And also looked at whether you can recover the heat that is in the oil for useful purposes. So there's still, if you don't do anything with it, this is a loss of the system. So if you can reuse the heat that is in the oil, you can improve the efficiency of the system. And finally, the zeotropic mixtures. That is a mixture of working media that you will do. As if you have a temperature glider application, you better use a mixture that fits better with your application. So we've done a lot of modeling on mixtures of hydrocarbons to see what kind of glides they are suitable, what kind of mixture you need for what kind of glides. That's been completed, and we'll start experiments on short notice to test a few of these mixtures in reality. Next slide. This is my last one, I think. Yeah, thank you very much. Any questions I'll take later, maybe, I guess. Thanks for your attention.
Thanks a lot, Simon. And now, SUSHEAT.
So this is Ruben Barbero. Thank you for the invitation to this webinar, and thank you all for being here. I'm going to introduce you SUSHEAT project. Next slide, please. It's an Horizon Europe project coordinated by UNED, by me in this case. The acronym means Smart Integration of Waste Heat and Renewable Energy for Sustainable Heat Upgrade in Industry. In the consortium, we are 14 partners coming from 10 different countries. Next slide, please. And this project is focused in the decarbonization of the industry. In this case, integrating heat pumps, thermal energy storage technologies, solar heat, and artificial intelligence control system, based control system. Our goal is to supply heat about 200 degrees to the industry. And the slide, please. So basically, we need to develop 3 key technologies, and a stirling-based high-temperature heat pump technology with a coefficient of performance up to 2.8, bio-inspired phase change material thermal energy storage system, and artificial intelligence control system. With these 3 technologies, we will be able to harvest solar thermal energy, waste heat, or even ambient heat, and upgrade this heat to 150 to 250 degrees. We will apply this solution to 2 cases that will be validated at laboratory facilities, and we will apply also this solution to this scaled-up solution to other 4 replication cases. Next slide, please. So basically, we will integrate this high-temperature heat pump, the bio-inspired thermal energy storage, and solar collectors, all of them integrated by a control system based on artificial intelligence to validate this solution at tier of 5 in a laboratory. Next slide, please. So this solution will permit us to test some different operation scenarios. So harvesting waste heat, ambient heat, or solar heat, and upgrade it or storing it before or after upgrading heat. So this different scenario will permit us to obtain a lot of conclusions about the operation of the system to generate solutions specific for any place, any location, any demand. So this will provide us a lot of information. Next slide, please. The heat pump that we will use is the HOET-10 heat pump from Energy, which uses helium, which is inert, non-toxic, 0 ozone depletion potential, and 0 global warming potential. So it is a very sustainable solution and will permit us to reach higher coefficient of performance that vapor compression cycles in some of the temperature ratios. Next slide, please. We had some challenge to face in this project. In the case of the heat pump, which are the designing of the ceiling and piston rings and optimizing the coefficient of performance for this range of temperature. You can see in the graph on the right the results obtaining for 200 degrees, even from ambient. For a load, partial load operation, the dashed line represents the expected result for the full load operation, and these are our objectives. That means a coefficient of performance of 1.9 at 250 degrees, sources from 70 degrees, and a coefficient of performance of 2.9 for a 1.2 Kelvin to Kelvin ratio. Next slide. So we will integrate also these two other technologies, thermal energy storage, which is bio-inspired, and it will build from additive manufacturing, 3D printing, and also we will develop a control system based on artificial intelligence that will permit us to integrate all this system in an optimized way, and also to develop different specific solutions for any location or for any demand. Next slide, please. We are now in October 2025, and we are approaching to critical state of the project. We will commission the installation at the end of this year, and we will start obtaining results about the integration of all this system. And we are on the pathway to our expected impacts. So thank you for your attention. It's all from my side. If you have any question, I'll be happy to answer them.
Thanks a lot. And the last one is Thunder.
Hi, hello.
Hello.
Can you hear me?
Yes, and we can see you too.
Perfect. So, good morning, everyone. Thank you so much for your time, and thank you so much for the invitation. I'm Luca Socci. I am a researcher of the Thermodynamics and Heat Transfer Research Group at the University of Florence. And today I present some insights of the Thunder project, in which my research group is involved in terms of modeling, numerical simulation, and experimental activities. Next one, please. So Thunder is a 48 months project that involves 14 partners from all across Europe. It is divided in 7 work packages, and the idea, the core is the valorization of waste heat from data center through scientific research and real application. Indeed, we will realize a demo site in Varna, Bulgaria. Next one, please. In Thunder, we will establish a chain in which waste heat is recovered from data center, transport, stored, and reused within a district heating network. And if necessary, the heat can also be upgraded to ensure that it matches the necessary thermal levels. Next one, please. This is the representation of the project concept, of the connection between the different technologies that we will analyze in brief. Next one. The heat recovery takes place through the cooling system, in particular when the mechanical compression cooling is active. So the recovery of the waste heat happens at the condenser of the refrigeration cycle. The recovery heat is the rejection thermal flux. Next one. Then the waste heat recovered from the data center is temporarily stored in a mobile unit that we have called heat on wheel. this heat-on-wheel solution is a storage that relies on phase change materials and that enables the transport of heat from the data center area to the district heating plant, where it will be used in a thermochemical storage. The thermochemical storage is truly the core, the most important part of Thunder project. So I describe briefly what is a thermochemical storage. It is a storage, this one, it's a storage that relies on materials that combine both heat and mass transfer processes involving the interaction between a solid and a gas phases. In summer, during the charging phase of the storage, heat is supplied to separate the solid component and the gas one. In winter, during the discharging phase, the gas is reintroduced in the storage and releasing heat. There is some advantage that make it highly attractive within the project framework. Next one, please. In particular, in Thunder project, the pair solid gas chosen for the thermochemical storage is a silica gel calcium chloride composite for the solid component and the water vapor for the gas component. So we have reaction of hydration and dehydration of the material. In the summer phase, the heat from the phase change material heat-on-wheel is used to charge the thermochemical storage and separate the solid and gas components, while in the winter phase, it is released from the thermochemical storage to feed the district heating network. Moreover, a fundamental role is played by high-temperature heat pumps. When it's necessary to rise the temperature of heat flows, we use this technology, both in the phase of charging the thermochemical storage from the PCM material, and both in discharging the thermochemical storage to feed the district heating. This is a list of what has been done so far with various type of activities, ranging from the general design of the concept to numerical simulation and experimental detailed test. In the next future, we will do in-depth simulation again, and in particular, we will build the demo site, the effective real-scale prototype, in order to improve the single technologies that we have in Thunder to enhance their diffusion towards the carbonization of data center and district heating sector. Thank you so much.
Thanks a lot, Luca.
Yes, I've added at the end only a brief description of our research group in Florence and how it contributes on Thunder.
Okay. Thank you. Okay, so now we have 5 minutes. If you have any question, you can ask them now to any project, and you can also write it in the chat if you want.
So, Anais, if there is no question, I was wondering whether I had to send email to some of the people that are attending Sustainable Places next week. So just to all of you, if you think I missed you, please send me an email so we can have a very quick meeting tomorrow if you can. So for next week event at Milan Sustainable Places.
Yes. Thanks. Okay, so we are going to send to those who register on the Google Meet form. You can still do it now if you haven't. The link is in the chat. We are going to send the presentation if you need the contacts or I don't know, and also the replay. Yeah, feel free to send us an email or to contact us, I don't know, LinkedIn, and we will be happy to answer your questions. Thank you so much to all of you for joining today. And thank you also to all the speakers, because you provide a very impactful insight, and thanks also to the audience. We hope you found this session inspiring and useful also, and that you are leaving with some new ideas to take forward. And yeah, stay connected with us, and we are looking forward to seeing you at the next webinar. We will send you an email, and we will post also on the social media. Take care of you, and maybe see you next time.
Thank you.
Bye-bye.
Bye-bye.
Thank you so much.
Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye. Bye. Bye.
Bye.